Hello class, welcome to this video on the Geometry EOC Review, Part 3. So let's go ahead and continue from where we left off. GR 2.3, identify a sequence of transformations that will map a figure onto itself or onto another congruent or similar figure. Number 1, which transformation maps a solid figure onto the dashed figure? So first off, let's go ahead and identify this point here. So it's going to be negative 3 and 1, right? That's what that point is, negative 3 and 1. And that's going to transform to, well, clearly it's going to go into this point, which is 3 and negative 1. And so based off of that rule, we can see that xy is being mapped. So what's happening is that the x is changing sign. So basically we had to add a negative in front of x so that the double negative turns into positive. And then the y is turning negative as well. And this is the rule for a rotation 180 degrees about the origin. And so that's what we're looking at. So you have to memorize those rules, right? So rotation 180, rotation 270, all that stuff. All right, number 2, triangle ABC and DEF are graphed on the set of axes below. Which sequence of transformations maps ABC onto DEF? All right, so in this case, let's go ahead and we know that C goes to F, right? So let's go ahead and just write the coordinates of C. The coordinates of C are negative 1 and negative 6, it looks like. So negative 1 and negative 6. And that's going to go on to F. And F is 1 and then 1, 2, 3, 4, 5, 6. Okay, so 1 and 6. And so you can see here that basically... so let's take a look. If I look at the first one, it says a reflection over the x-axis followed by a reflection over the y-axis. So if I take C and I reflect about the x-axis, then what that's going to do is it's going to change the y value from negative to positive, right? So the rule for x-axis rotation or reflection is that the y changes to its negative, right? That's for x-axis. And then the rule for the y-axis is that the x changes. You just put a negative in front of the x. So this is going to turn into negative 1, 6. And then if I were to do the y-axis, which is what this problem says, part A, then the x is going to change, right, to its positive counterpart. And I get 1, 6. Now, is that what I should have gotten? The answer is yes, that's what I should have gotten. So that is my answer. That's going to give me my answer for F. So that looks to be consistent. All right. So it happens to be the first answer, so we're done. That's good. Number 3, a triangle has vertices at A, B, and C. Which transformation will produce an image with vertices 3, negative 1? Okay, so we're going from A to A prime. So let's just use those coordinates just to make it a little easier. So if I look at that, well, this is going from x, y. Looks like the x there's a negative, there's a sign change. So you have x changing sign, and then y stays the same, right? You can see that the y stays. So this is the rule. This rule is a reflection about the y-axis. So the answer is F. Number 4, what are the coordinates of each vertex if the triangle is translated 4 to the right and 6 down? So all you have to do is add 4 here and subtract 6. And that would take it 6 down and 4 to the right. 4 to the right, 6 down. 4 to the right, 6 down, and so on and so forth. So if I did that, well, my A prime is going to be negative 7 plus 4 is negative 3. 6 minus 6 is 0. 4 plus 4 is 8. 9 minus 6 is 3. C is negative 2 plus 4 is 2. Negative 6 minus 3 is negative 9. The answer is D. All right. Ken stacked 2 number cubes. Each cube was numbered so that opposite faces have a sum of 7. All right. Which transformation did Ken use to reposition the cubes from figure P to figure Q? So this is going from here to there. All right. Well, if this is 2 here, that means the face on this opposite side, on the back, is 5. And then the face here on the opposite side of the 3 is 4, right? And so notice that this is 4 on this side, and then on this side here on the back is 2, right? Because 2 plus 5 is 7. So what that says is that this got rotated this way. So that way the 2 is now here, and then the 3 is now here. It got rotated 90 degrees. So it looks like it got rotated 90 degrees, the top one. And then for the bottom one, this is 2, so this is 5 over here, and that's 3, so this is 4 over here. And then so notice that the 5 used to be on this side, and now it's on this side, right? So it looks like it got rotated 180 degrees here. So the top got rotated 90 degrees clockwise, and then the bottom got rotated 180. So the answer is B. All right, number 6. Which composition of rigid motions will map one triangle onto another? All right, so first off, in order to get, so notice that C goes from being on top to being on the bottom. So that's going to be some kind of flip, right? So what we're going to do is we would have to flip, that's C right there. It's not showing up on there, but we would have to flip this. There you go. So we'd have to flip it so that C is on the bottom, right? And D is on the top, so we're flipping everything, and then B is on the bottom, and then A is on the top. So something like that. So when we flip it, it'll go like that. And then we can just translate it so that they move, right? So we flip it and then we translate it. So a reflection followed by a translation seems to work. All right. This one we can skip because there's no honors standard that I included. All right, so we're looking at 2.5. Given a geometric figure and transformations, draw the transform figure on the coordinate plane. All right, so a lot of these are repeat types of questions. It's just the same skill. So I'm going to kind of go through these as fast as I can. So we need to write down all the coordinates and then apply the correct rule. Reflection across the y-axis. Let's write down that rule. So if I want to reflect across the y-axis, then the x has to change to its negative counterpart, the opposite sign. So that's transformation number 1. Transformation number 2, we are rotating 180. So that rule is as follows. The x and the y coordinates, you put a negative in front of the x and the y coordinates essentially. So let's go ahead and do that. Let's do that for TUVW. So what I'm going to do is I'm going to just write down the coordinates. You guys are going to draw them. So I'm not going to draw the shapes. You just draw them on the paper. All right. I'm just doing the coordinates. All right. And then you can easily just graph them afterwards. All right. So T is 14 and 13. U is 11, 7. V is 5, 4. And W is 8, 10. And so what we're going to do is we're going to do the transformations. So we're going to do the first transformation. So the first transformation is the x has a negative in front of it. So we're going to put a negative in front of the x. All right, and then we're going to do the second transformation now, the final transformation. Then we're going to put another negative in front of the x, and then a negative in front of y. Now, if I put a negative in front of the x here, this turns into double negative, which is positive. And then the y doesn't have any negatives, so it's going to turn negative. So these are going to be as follows. All right, and those are my coordinates for T, U, V, W prime. So you can go ahead and graph them and get your shape. All right, but just for the sake of time and for this video, the length of this video, I'm going to keep going. All right, so we got rule number 1, number 2. So the rule for this is you're going to take the coordinate and you're going 1 to the right. So that means you're going to add 1 to the x. You're going 16 up, so you're going to add 16 to the y. And in this rule, 270, you swap the x and the y positions, and then the new x position, the second coordinate, is going to have a negative. All right. So we're going to go ahead and do that. We have kite h I j k. I should probably not do it on the graph just in case the shape goes there. So let me get rid of those. Let's do it over here. H I J K. So h, so the coordinates of h are -11, -10. Coordinates of I are -7, -14. Coordinates of j are -5, -10. K, -7, -6. All right, so let's do the first transformation. So for the first transformation, we have to add 1 and then add 16. So +1 + 16. So -11 plus 1 is -10. -10 plus 16 is 6. -7 plus 1 is -6. -14 plus 16 is 2. -5 plus 1. -10 plus 16. -7 plus 1. -6 plus 16. All right, that's how we get those coordinates. All right, and then for the second rule, so for the second rule, we have to switch the x and the y and then put a negative on the second coordinate. So switch the x and the y here and then put a negative on the second coordinate. But the second coordinate, this 10 had a negative already, so if I put an extra negative, it turns positive, right? So therefore, it becomes 610. So switch the coordinates here, but then put a negative on the second coordinate, but that's already negative, so that turns positive. All right, so I'm going to keep going and apply that rule, and I get these coordinates. So those are my coordinates, so make sure to go ahead and graph them and get your answer. All right, so number 3. We have H, I, J. Let's write down the coordinate transformation rules. So 270 clockwise, we did that one already. You switch the x and the y, and then put a second negative on the second coordinate. Now for the reflection across line x equals 1, I will tell you the rule for that, just to make things a little simple. So the rule for that is, because you're reflecting about x equals 1, right? That's a vertical line. That means when you reflect, it's going to change the x coordinate, but not the y coordinate, right? So the x coordinate change is as follows. The rule is 2a minus x, comma, y. All right, so that's the rule. In this case, the a is equal to 1 because that's the the line here. The line is x equals 1. So that's a, okay? A is 1. So in this case, the rule is going to be 2 times 1, which is 2. So it's going to be 2 minus x, comma, y. That's the transformation rule for reflection across the line x equals 1. So I'll write down both transformation rules just in case. Actually, yeah, so I'll write them both down so you have it. So if I'm reflecting across y equal, if I'm reflecting across x equals a, then the rule is as follows, the rule that I wrote down earlier. If I'm reflecting across y equals a, y equals a number, then the rule is like this. The y changes, but not the x. It's going to be 2a minus y. So those are the reflection rules for x equals a and y equals a, in case you wanted to know them. All right, so let's go ahead and transform these coordinates using those rules. So g is -6, -9. Okay, go ahead and zoom in a little bit. All right, so -6, -9. H is -4, -5. I is -8, -3. And J is -10, -7. Okay, so we're going to apply the first transformation. So first transformation is you switch the coordinates, and then the second one has a negative. So I switch it, so it's going to be -9, -6. Then put a negative on the second coordinate, but then that turns it into positive. So it's just going to be +6. And then do that here, do the same thing here. -5, -4, but then double negative turns out to positive. -3, -8, but then double negative turns out into positive. And that's your first rule. And then we'll go ahead and transform this one more time. So then we're going to, all right, so in order to do this one, we need to use this rule, 2 minus x. So it's 2 minus -9. Let me do that over here. So 2 minus -9 is 11, right? And then for this one's 2 minus -5 is 7. 2 minus -3 is 5. 2 minus -7 is 9. So the x coordinate is going to be 11, 7, 5, 9. And then the y coordinate is going to remain the same. Okay? And those are your coordinates for G prime, H prime, I prime, J prime. And then you can go ahead and graph them. All right, number 4. So this is transition 16 left, 1 down. So the rule is as follows. Since you're 16 to the left, you have to subtract 16. 1 down means you subtract 1 from the y. That's rule number 1. And then rule number 2. Since you're reflecting across y equals x, you just have to switch the y and the x, and that's how you transform it. Okay, so we got G, H, I, J for the coordinates. So G is 9, 5. H is 13, 9. I is 9, 13. And J is 5, 9. All right, so let's transform the first using the first transformation rule. So we're going to subtract 16 and then subtract 1. So we're going to do -16 minus 1. So 9 minus 16 is -7. 5 minus 1 is 4. 13 take away 16. 9 take away 1. 9 take away 16. 13 take away 1. 5 take away 16. And then 9 take away 1. Yeah. -11 and then 9 take away 1. All right, so then we're going to transform it one more time. And let me just erase this circle here. All right, so now we're going to switch the x and the y coordinate, and that is it. So 4, -7, 8, -3, 12, -7, 8, -11. And those are your coordinates. And then you can go ahead and graph them, get your final image. All right. So next page, apply rigid transformations to map one figure onto another to justify that they're congruent. All right, so which transformation maps a solid figure onto the dotted figure? That's pretty straightforward. That's just a reflection, right? If you reflect it and flip it across this line, you're going to get the same image there. Select all rigid motions that describe the pre-image and image shown. Okay. So first off, in order to get from here to there, that's what we want to do. Let's check part A. Rotate 180. So if I were to take that and I were to rotate it 180, that means, let's say I want to rotate it 180 here. If I rotate it 180, then this is going to go over here, and that's going to be 180. Then if I rotate this, then that will be over here. That makes it 180 degrees, right? Then if I were to take this part and I rotate it 180, then it would go here. Then if I were to take this part and rotate it 180, right, with the same distance, then that part will go kind of like this. And then you can kind of see how the figure is gonna, the drawing's gonna end up, right? It's gonna basically go, it's basically gonna look like this. So that's gonna rotate 180, that's good. That's gonna match up with that. Glide reflection. A glide reflection is when you reflect something about a line, for instance, and then you slide it over. That's what a glide reflection does. But if I reflect it, it's not going to give me that image, so I'm not going to select that. That's what a glide reflection is. You reflect it and then you kind of glide or slide it down, and that parallel to the where you reflect it. Rotation 90 degrees, no, because we need to rotate 180, so that's not going to work. Reflection across the horizontal line and then rotation of 90, no, not rotation 90, because that's not, we've said it's got to be 180. Reflection across a vertical line and then reflection across a horizontal line. All right, let's take a look at that. If I reflect across a vertical line, then it's gonna, then when I reflect it, it's gonna be the mirror image of that. So it's gonna look kind of like that, right? And then if I reflect that across the horizontal, then it's gonna be a reflection of that. And so it's gonna look like, it's going to look like that, which is exactly what this is, right? So that is also true. Okay. Looks like we got A and E are the correct answers. All right, number 3, which triangle is congruent to triangle PQR? State which sides, a pair of sides are congruent. All right, so this is not too bad. If I were to look at this one, let's take a look at this. Okay, so the sides are 2 and 1. That's 2 and 1 like length. This length is 1 and 3. This length is 2 and 3. If I check this side, this length is 1 and 2. This length is 1 and then 3. This length is 1, 2, 3, and 2. Ooh, that looks like it matches perfectly. 2, 3, 2, 3, 1, 2, 1, 2, 3, 1, 3, 1. So these must be congruent to each other. All right. So notice that the PQ side matches up with the, what is that side called? That's FD. The PQ side matches with the DF side, right? So so PQ matches with DE. All right. So we're gonna say PQ is congruent to DE. And then the RQ side matches the FE side. And then this side obviously has to match because that's the leftover side. That's congruent to the FD side, or the F. All right, so those are the pair of sides that are congruent. And oh, we're going to list the triangles that are congruent. So we're going to say triangle PQR is congruent to, so P goes with D and R goes with F. All right, so it's going to be triangle DEF. All right, so number 4, the vertices have those coordinates of a triangle. Under which transformation is it not congruent? This is a repeat of what was in the page 12, so I'm not going to go over that. That's what we did in page 12 in a previous page here. All right, this is an honor standard, so we can skip that, and we'll go to the next page. So we'll go to page 18. GR 2.8, apply an appropriate transformation to map one figure onto another to justify that the two figures are similar. That's a typo. It should not be a D there. All right, so in the diagram below, triangle ABC is similar to triangle DEF. If AB is 6 and AC is 8, which statement will justify similarity by A or SAS? Okay. So we know that this is proportional to this, and this is proportional to this side, right? So let's go ahead and say, okay, so if this, for part A, let's say that DE is 9, if that's what they say. DF is 12. And let's see if that's true. And obviously they say angle A is congruent to angle D. So that means we have an angle that's the same. In that case, 6 is proportional to 9. So 6 is proportional to 9 as 8 is proportional to 12. And so we can set that for that proportion up. And then we're going to cross multiply to see if that's true. So 6 times 12 is 72. 9 times 8 is 72. So this is true. That means that we got a side and a side here, that those are proportional. We also have an angle in between them. So by SAS, they are similar. So looks like this is going to justify similarity by SAS. So the answer is A. All right, number 2, in the diagram below, triangles XYZ, UVZ are drawn such that angle X is congruent to U, and then the XYZ, XZY, and UZV are similar, or the congruent, sorry. Describe a sequence of similarity transformations that shows that the triangles are similar. All right, so similar means that, we want to show that they're similar, so we want to do transformations that will make them overlap. So in order for this to overlap, I'm going to rotate this. If I rotate that, then this angle is going to match up with that angle, right? If I rotate it, and that's exactly what I want. So when I rotate it, they'll kind of look like this. I'll have Z, I'll have X, and I'll have Y. Can you guys see that, hopefully? If I rotate it, then I get something like that. So rotation about point Z. So rotate about point Z. And then the next transformation we could do is to make them overlap. We want to stretch this out. So we want to do a dilation. So we want to do a dilation. More specifically, a stretch. And then when we stretch it out, we could stretch it out, and then it'll overlap. So we're going to do a dilation. In this case, a stretch. And that will make it overlap, and that will prove that they're similar. Okay, so when two triangles are considered similar, when are two triangles considered similar but not congruent? So they're considered similar if the distances are proportional. So the distance between the vertices are equal? No, that makes it congruent. If the distance between vertices are proportionate? Yeah, that's what we're looking for. Number 4. The vertices of triangle JKL are given. Find the coordinate pairs of the vertices for each of the dilations with a scale factor of 5. All right, so the dilation about the origin, I'm going to give you the rule for that. So this is the rule for dilation about the origin. Dilation about the origin, the rule is you multiply by the scale factor K. K is, in this case, 5, right? So in this case, K equals 5. So in this case, it's going to be 5. The rule is going to be 5x and then 5y. Okay, so all we got to do is transform these. So if I multiply this by 5 and multiply this by 5, that's what we're going to do for all of them. Okay, so negative 3 times 5 is negative 15. Negative 2 times 5 is negative 10. K is going to be 1 times 5 is 5. 4 times 5 is 20. And then 4 times 5 is 20. 2 times 5 is 10. And that is it for part A. Part B is the more complex one because you're dilating about point J instead of the origin. So there's no specific rule for that. I mean, there is a rule, but it's a bit complex to write down. So I will actually just show you the drawing for this. So we're going to actually draw this out, okay? All right, so we have here J is -3, -2. K is 1, 4. And L is 4, 2. Okay, so we're going to do, so here's the triangle, the original. And we want to dilate about point J, which means that J is going to remain the same. Because J, if you're stretching it from J, then J is going to stay the same. So we know that J is going to stay the same. That one is easy. J is easy. Now K, on the other hand, K and L, we have to work for it. So if I want to go from J to K, well then I have to go up. Looks like 1, 2, 3, 4, 5, 6. I have to go up about 6. Right? So I have to go up about 6. And then I have to go over 1, 2, 3, 4. Right? And then we're going to stretch this by a factor of 5. So we're going to stretch it by a factor of 5. So we're going to multiply each of these by 5. So this is going to be 30 and this is going to be 20. So this vertical distance has to be 30, this other one has to be 20, and that's it. That's what will stretch it beyond what it needs to go. Okay. And then for L, it's gonna, to go from J to L, I need to go up how much? 4. And I need to go over, if I have to count it, 7. Looks like we have 7. 1, 2, 3, 4, 5, 6, 7. Yeah, I need to go over 7. And then I'm going to multiply those by 5. So it's going to be 35 here. And then 4 times 5 is equal to 20. So that means I would have to go stretch it by 20 and then stretch it by 35. All right. So in order to get K, all I have to do is take the coordinates of J, right, which is -3 and -2. So take the coordinates of J, and I would have to stretch it. I would have to add it to 35 because I need to stretch it in the X direction by 35. So I'm going to add 35 to that. And I'm color coding this so you can kind of tell. And then I have to do I have to take the Y coordinate of -2, and I have to add 20 to it because I need to go up 20 from there. Okay, and that's how I get. Oh, that's for L. I'm sorry, that's not for K. That's for L. Sorry. All right. So then L. I guess I should call this L prime, right? So I got J prime. L prime is going to be 35 minus 3 is 32. And then 20 minus 2. So this is going to be 32 and 18. So those are the answers for L and J. And then K, you're going to take the J coordinates, -3 and -2, and you're going to add 20 to the X coordinate because you got to go to the right 20 because of that little stretch factor. And then the Y coordinate of J was -2, and we got to add 30 to it because we got to go 30 up because of the stretch factor of 5. Okay. So in that case, K prime is 27 and it's 28. All right, and those are your new coordinates. And if you were to draw them, you can see it'd be really big. It'd be stretched by time from J. All right, this is an honor standard, so thankfully we do not have to do that page. So you can skip over to the next page, page 20. All right, so 3.1, determine the weighted average of 2 or more points on a line. Okay, so the formula for weighted average, I'll write it down. In fact, I'll just write it down over here because we're going to be often, is x equals, if you want to find the x coordinate of the weighted average, you just take the x1 coordinate times w1, that's w is the weight, and x2 times the weight 2 over the sum of the weights. So that's why it's called weighted average, is because there's a weight assigned to each point. Okay, so on a number line, r is at 12 and t is at -6. So we got t over here, we got r over here. And t is at -6 and r is at 12. Okay, so where is r going to, or where is, find the coordinate of the point on RT that represents the weighted average. So there's going to be a point somewhere on here. And then they said that r has a weight of 1/6. So let's call this point x1. And let's call this point x2. And let's call the weight w1 and then the weight here w2. Okay? And we're just going to plug that into the formula. That's all we're going to do. X is equal to x1 is -6. That's the x coordinate of t. Times w1 is the weight of t, which is 5/6. Plus x2 is the coordinate for r, which is 12. And then w2 is the weight of r. The weight of r is 1/6. Over w1 plus w2. There you go. Just using that formula there. That's all you have to do. Just plug them into that formula. All right, and then 5/6 plus 6 plus 1/6 is 6 out of 6. And we know that 6 out of 6 is just 1, right? So I'm just going to change that 6 out of 6 to 1 whole. All right, so this is going to be 1 basically on the bottom. And then, okay, so for -6 times 5 over 6, well, -6 times 5 is -30. And so this is -30 over 6. And then 12 times 1 is 12. You just multiply the numerators. So 12 over 6. 30 divided by 6, -30 divided by 6 is -5. And then 12 divided by 6 is 2. So -5 plus 2 over 1. The 1 doesn't do anything, so I'm going to ignore it. -5 plus 2 is -3. The answer is -3. Okay, let's do a little bit more practice with that. Find the coordinate of P on AC that would represent the weighted average if the weights are 3/4 and 1/4. All right, so this is x1. We'll call this x2. x1 is -5, x2 is 7. And then we'll just use the weights for w1 and w2 here, okay? So x is equal to x1, which is -5, times w1. w1 is point A, so that's 3/4. x2 is 7. Then the weight, the w2 is 1/4 over w1 plus w2. Again, 3/4 plus 1/4 is 4/4, which is 1, okay? And the 1 doesn't do anything, so I'm going to ignore it, okay? -5 times 3 is -15, so we got -15 over 4. Plus 7 times 1 is 7, so 7 over 4. Add that together, -5 plus 7 is -8 over 4. Remember, do not add the denominators. When you add two fractions together, you just add the numerators. -8 over 4 divided by 4 is -2. Let me make sure I added that correctly. All right, so that means P has to be over here. P has to be at -2. And if you think about it, that kind of makes sense, because this one is what, 1, 2, 3 spaces away. This is 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces away, right? So this is 3 12s, because 3 plus 9. And then this is 9 12s. Well, 9 12s is 3/4, and 3 12s is 1/4. So that makes sense, okay? So that's just to check my answer, to see if that makes sense. All right, so number 3, find the coordinate of P that represents the weighted average of points F and H when point F weighs 3 times as much as point H. All right, so F weighs 3 times as much as point H. So let's go ahead and just say, let's call this X1 and let's call this X2, right? And then, so W2 is going to be the weight of H, right? So let's call the weight of H 1. And in that case, because they don't tell us the weight, so let's just say that H is 1, the weight. And then that means that the weight of F has to be 3 times 1, which is 3, because it's 3 times as big, right? So 3 times 1 is 3. All right, so in that case, that just makes the calculations a little simple. So we get X is equal to X1, which is -2, times W1, which is 3, plus X2, which is 5, times W2, which is 1, over W1 plus W2. So -2 times 3 is -6. 5 times 1 is 5. 3 plus 1 is 4. -6 plus 5 is -1. So we have -1 over 4. -1 over 4. -1 / 4. Just in case they give you a grid and option, at least you know how to fill that in. All right, so that takes care of page 20, guys. So we're moving on to page 21. Given a mathematical context, use coordinate geometry to classify. All right, so given a mathematical context, use coordinate geometry to classify or justify definitions, properties for circles, triangles, or quadrilaterals. All right, so number 3, select all the statements that are true. All right, so this one's going to be kind of interesting because they don't give us any numbers here. We just have to use the variables in order to determine like stuff about the shape. So it's kind of interesting. It makes it a little bit challenging, but you know, if you just kind of follow along, you know that so we want to say that AB is equal to CD. Let's see if that's true. So we want to see, is AB equal to CD? So we have to use the distance formula, okay? So to get AB, remember the distance formula is x2 minus x1 squared plus y2 minus y1 squared. So that's the distance formula, just in case you forget. Just in case you forget that formula, let me just put it in a bubble, I guess. All right, so to get AB, we have to take the square root of and subtract the x coordinates, subtract the y coordinates. So we got a minus 0 squared plus b minus 0 squared. So that's square root of a squared plus b squared. So that's AB. And then we have to see if that's the same thing as CD. So CD equals square root. So we got to subtract the coordinates, right? So we got to do C minus A, right? So C minus A squared plus, and then 0 minus B. Okay, so C minus C cancels. And then negative becomes positive, so it becomes A squared. And then 0 minus B is negative B squared. But remember, negative b squared is the same thing as b squared because it doesn't matter if it's negative. If I square a number, it's going to be positive anyways. So we might as well change this negative into positive. And so these are the same, okay? So they check out. So this is true. AB is equal to BC. Let's check that out. To get BC is just, well, the way to get the length is just to subtract the x coordinates, right? The x coordinates are a and c minus a. So that's all you got to do is subtract those x coordinates. That's because this is going straight, right? It's going, you know, straight from left to right. So subtract the x coordinates, c minus a, which is c minus 2a. Okay, so BC is c minus 2a, which is not the same as AB. So that's not true. Let's do AD. AD is BC plus 2A. We just said that BC was C minus 2A. And then we're going to add 2A to that. But notice that the 2A's cancel, leaving you with C, right? Okay. So we get C for that. However, is that the same thing as AD here? Well, let's see. If I were to do the distance from here to here, well, the distance is going to be C because it's C minus 0, right? C minus 0 is C. So that's this distance right here. So yeah, that's true. So it should be equal to C, and that's exactly what we got. And then finally, we're going to see, are they parallel? Is AB parallel to CD? Let's find out. So let's do the slope of AB. Remember, slope is rise over run. So in this case is you got to subtract the y coordinates. So let me write the slope formula. y2 minus y1 over x2 minus x1. Okay. So we got b minus b. Those are the two y coordinates. Or no, that's for BC. I'm sorry. It's the slope of AB. AB is so y minus y, b minus 0 over x minus x, so a minus 0. So that's b over a. All right, and then the slope of CD is b minus 0 over c minus a minus c. Which the c's cancel, so you get b over negative a, which is not the same thing as that. Remember, for two lines to be parallel, they have to be the same. So this is not true. Okay, next we're going to determine is AD parallel to BC. Well, notice that this line is flat, so the slope is 0. And you can determine that easily. So the slope for AD, if you're to subtract the y coordinates, is 0 minus 0 divided by c minus 0. And 0 divided by anything is 0. So that slope is 0. The slope of this guy is b minus b over c minus a, right? But b minus b is 0, and 0 divided by anything is 0. So the slopes are, so these are parallel. And you can tell that it's parallel, but this is just proving that they're parallel. All right, so those are the answer choices for number 1. Okay, all right, so number 2, the vertices of the triangles are given. What type of triangle is it? All right, so we got a triangle DEF, and we need to basically find all of the sides, the length of all of the sides, to see if it's equilateral or isosceles or whatever. So let's use the distance formula. Let's do DE first. So DE equals square root. So this is DE. Subtract the x coordinates, subtract the y coordinates. So we got 16 minus 1 squared plus negative 1 minus 19 squared. And then next we'll do EF. Square root. Subtract the y coordinates, negative 8 minus negative 1 squared plus negative 8 minus 16 squared. And then finally we'll do FD. So F and D. So negative 8 minus, hold on a second. I did the y coordinates first, but it doesn't really matter if you do y coordinates or x coordinates first. It doesn't, just so you know. But I like to do the x coordinates. I'm not sure why I did y coordinates here first, but it doesn't matter. It's still the same thing. So negative 8 minus 1 squared and negative 8 minus 19 squared. Okay, so in any case, if you do this on the calculator, and you could just do it on the calculator, you get 25 here. Here you get 25. Here you get 28.46. So clearly two of the sides are the same. And so we could say that the triangle is isosceles. All right, that's how you do that. Number 3. The vertices of GHJK are given. What is the most precise classification of GHJK? All right, so let's go ahead and graph it because that's probably the best way to check it out. Okay, so let's go ahead and draw it. All right, so we got negative 1, 0. H is 1, 2, 3, 4, 5, 6. J, and then we got 5 and then 2. All right, so this looks like a kite, right? So we're going to need to prove that it's a kite. So to prove that it's a kite, we need to prove that these two are congruent and then these two are congruent. Okay, so that's what we need to prove. We don't know that yet. So I'm going to erase them now. All right. Oops, I didn't mean to do that. Okay, I'll just go back and draw it. All right, so let's go ahead and prove that. So that's actually pretty easy to do for HJ and JK, because the distance from H to J is, well, 1, 2, 3, 4. The distance from J to K is 1, 2, 3, 4. You just got to count the number, the number of jumps. So those are clearly the same. That's easy. Now GH and JK and GK we can find by looking at the jumps. 1, 2, 3, 4, 5, 6, and then 1, 2. That's 2 jumps. 1, 2, 3, 4, 5, 6, and then we got 1, 2. That's 2. You can also do it with the distance formula, right? So if you were to use the distance formula, you get 6 squared plus 2 squared, and then GK, you get the same exact thing. Okay, this is the same thing as distance formula. This is just the visual version of the distance formula, but you can see that the distances are all the same. So that means these two are the same. Okay, so this is just a visual way to look at it. So therefore, it is a kite. The kite is defined as a quadrilateral where the two sides next to each other are the same, and you have two pairs that do that. Okay. All right, so number 4, if you're given the coordinates A, B, C, and D, select all the ways you can prove that it is a rectangle. So I'm just going to draw each scenario out just to kind of show you. So this is rectangle A, B, C, D. Be very careful. Rectangle A, B, C, D, you have to trace it, and that's the order that you do it in, okay? So as long as you do that, then you should be fine. So to prove that the ABCD is a rectangle, it says show that AB is parallel to CD, and then BC is parallel to AD. So far so good. That just shows that it's a parallelogram, not a rectangle. And then we want to show that AC is perpendicular to BD. That's what they're saying. And that is going to be incorrect. A rectangle never has perpendicular diagonals. Okay, the only time a rectangle has perpendicular diagonals is if it's a square. Okay, so this is sometimes true. This is not always true in general. So this is not going to be our answer choice. Next one. Use the distance formula to show AB is equal to CD, BC is equal to AD, and AC is equal to BD, meaning the diagonals are the same. So like these two are the same. This is true. By showing this, the opposite sides are the same, you've proven that it's a parallelogram. And then by proving that the diagonals are congruent, you've proven that this parallelogram is a rectangle. So that is true for the second one. Use the distance formula. So let me draw this out. ABCD. Use the distance formula to show that AB equals CD, and BC equals AD, and use the midpoint formula to show that the midpoint of AC and the midpoint of BD are the same point. That is not going to be true for a rectangle, or that is not going to be true for, I guess I should say that that's only true for parallelograms. A rectangle is a parallelogram. However, the fact, you're just proving that it's a parallelogram. You're not proving that it's a rectangle by doing this. Okay, so the midpoints being the same point only proves that the two sides are the two diagonals are cut in half. But remember, in a rectangle, all of the diagonals are the same. So all of these would be the same. So you're not proving that it's a rectangle. You're just proving that it's a parallelogram. Okay, so I'm going to cross that out to show you that that's the incorrect statement there. Use the distance formula to show that AB equals CD. Okay, so let's do that one. So AB equals CD, and then use the slope to show AB is parallel to CD, and then AB is perpendicular to BC. Okay, is that going to show that it's a rectangle? Well, the short answer is yes, right? And the reason why is because by proving that these two sides are the same and then they're also parallel, you've proven that it's a parallelogram, because you've proven you can use the fact that they're parallel to prove that these are congruent. Okay. I guess I can quickly explain that. I can quickly explain that reasoning before we end the video after this part. Okay, so the reasoning is that, and let me just get rid of the right angle here, is this proves that it's a parallelogram with these two details. Because if I were to draw this line through this, I make two triangles. And by making these two triangles, we know that these two triangles share this side in the middle. And so by reflexive property, it's congruent to itself. And because these two these two lines are parallel, that means the alternate interior angles are congruent. These are alternate interior angles. And therefore, these two triangles are congruent by side, angle, side, side, angle, side. And therefore, by CP/CTC, because the triangles are congruent, that means the corresponding parts are congruent. So we can say that those are congruent. And then therefore, we've proven that it's a parallelogram. Okay, so that's the quick explanation for that. So we've proven that it's a parallelogram, and then by proving that this is a right angle, well then we know that in a parallelogram, the angles here are supplementary, and the angles here that are opposites are congruent. And so if that's 90, then this is 90. And then because they're supplementary, if this is 90, this is 90, and if this is 90, this is 90. And then therefore it proves that it's a rectangle. So that's the reason why. All right, so use this for the last one. Use the slope formula to show that AB is parallel to CD. Use the distance formula to show AB is congruent to CD. AC is congruent to BD. So AC is congruent to BD. So remember, I told you that these two things prove that it's a parallelogram. And then the fact that the diagonals are congruent proves that the parallelogram is a rectangle. So that is true. All right. So let's finish up this last one, and then we'll call this part 3 for the end of part 3. Given the coordinates given, which coordinates for D make ABCD a square? So let's go ahead and just draw real quick just to make it fast here. 1, 2, 3, 6. So this is A. This is B. 5, 6, 7, 8, 9. And this is C. And then D is somewhere here, but we don't know where D is, right? And we know it has to be somewhere around there for it to be a square, right? So where is D going to be located? Well, because a square has right angles, right? That means that this has to be a right angle. For it to be a right angle, that means that it has to be perpendicular. So remember, two lines are perpendicular if their slopes are reciprocals of each other. Okay, so we need to figure out the slope of AB, the slope of all of these, basically. All right, so slope is rise over run. So here, the rise is what is that rise? Is 4, and then it goes over 2. This is 2, and then it goes over 4. Well, actually, we don't know that actually, because that's just a guess. That's just my guess for D. But we know how to do BC. BC is 4, and then it goes up 2. And then, okay, to get from A to D or D to C, for this to be perpendicular, for these two to be perpendicular, well, then the slopes have to be like opposite and reverse, right? So the slope for AB is negative 4 over 2 because it's going down, right? Remember, slope is rise over run. So rise is 4, run is 2, but it's going down, so it's negative. So the slope of AB is negative 4 over 2. And for it to be perpendicular, the slope of the other guy has to be positive 2 over 4. It has to be flipped and the signs have to change. So that means it has to go rise 2, run 4. And that's how you find D. Okay, so from A, you're going to go up 2. And then you're going to go over 4. So that means X is going over and up is going to the Y. So the coordinates are going to be 7, 8 for D. It's 3 plus 4, 6 plus 2. All right. All right, guys, that's going to do it for the video. I hope you found this useful and informative. As usual, I'll see you in the next part.